Newton's laws. This is an assignment we complete in class to identify what is pushing or pulling on what. So we name everything that has a push or a pull and what it is pushing or pulling on. For example, the first one says a person standing on the ground. Well, the ground is going to be pushing upward on the person, and the person is going to be pushing downward on the ground. If you think about holding a tennis ball, the tennis ball is pushing down on the hand, that's why you feel it, and then the hand is pushing up on the ball, preventing it from falling. For a baseball hanging on a string, the string is pulling up on the baseball, and the baseball is pulling down on the string. Now, in each one of these scenarios, we also have gravity. Gravity of the earth is pulling down on each object. Now, something we'll probably discuss later is going to be that the mass of an object is what gives it its gravity. So if a person is being pulled by the earth, then because the person has mass, it also has gravity. So the person is pulling on the earth as well. So the earth is pulling on the person is pulling on the earth. Now, with all of these examples, you can see that there's a pattern that's forming from this. We'll take the last example, two people leaning against each other, person A and person B. Person A is pushing against person B as they're leaning, and then person B is pushing back in the opposite direction. And the pushing and pulling, that's referring to as force. And since you look at each one of these scenarios, each one is pushing and pulling on each other, like the baseball is pulling on the string is pulling on the baseball. You can also see that the two forces are pulling in opposite directions. So when you're pushing or pulling, when you're identifying the two forces, they're also in opposite direction. This refers to as Newton's third law. For every force, which is considered a push or a pull, there exists another force that is opposite and equal. Now, the opposite refers to the direction. So if one force is pushing up, the other force is pushing down. The equal means that they're equal in magnitude, and there's a demonstration that we do in class to show that when you have two force sensors that are pulling against each other, the amount of force that each one has is going to be equal. Forces are also married, so no forces actually occur by themselves. You don't create a force without creating another force. For example, if I push on the table, I'm going to be pushing on the table, so I'm creating that force, but the table's pushing back on me. You have to have that other force that's going to be along with it. Now, there's a demonstration I also do in class with two carts where the carts are pushing on each other. Well, you don't expect one cart to move while the other cart just sits there. The reason is that other cart is feeling the force as well, so it gets pushed in the opposite direction. So in talking about Newton's third law, we have the ground pushing on me and me pushing on the ground. So I'm pushing down on the ground's pushing up on me. This is referred to as the law of action-reaction. So for every force, there's an equal and opposite force. For every action, there's an equal and opposite reaction. This is a demonstration on Newton's third law. So what I have here is I have two force sensors, and you can see these two force sensors as I pull them apart. They are taking their measurements right here. All right, so as I pull these apart, I want you to see, and I'm actually going to graph along this logger probe. It's going to graph the force of each one. And the main idea behind Newton's third law is that amount of force that the one photosensor has on the other, and the force sensor, the first one back on the second, is going to be equal and opposite. All right, so let's go ahead and do this. So we apply the forces. And then we pull a little bit more, and then we do something crazy. And then back over here. All right, back and forth. All right, and what you can see is the entire time, as one object was pulling on the other, whether they were both stationary or I was moving around, you can see that the force of the blue force sensor and the red force sensor, they matched each other the entire time. Even when it got crazy over here, everything still matched as it went back and forth. All right. So that's Newton's third law, that for every force that is being applied between these two force sensors, when one force sensor applies a force on the other, and then the other back on the first one, the two forces are equal in amount, but opposite in direction. Newton's first law talks about an object in motion or an object at rest. An object that is in motion will stay in motion if there's no outside net force. Now the key there is outside net force. You can have forces acting on an object and still keep an object moving, but you can also have no forces acting on it. Likewise, an object at rest will stay at rest until an outside net force is applied to it. So an object that's sitting on, let's talk about your book, a book sitting on the counter. The book is at rest and it has a lot of forces acting on it. It's got the table pushing up on it, it's got gravity pulling down on it, but all of those forces are balanced, so the net force is going to be equal to 0. This is called the law of inertia. Inertia and mass are essentially the same thing. The more mass an object has, the more tendency it has not to want to change its motion. So an object that is moving, that is in motion, will stay in motion, and it's harder to get it to change its motion if it has more mass. So an outside force that's being applied to an object that's in motion will change its motion, and we call that acceleration. So with that being said, what we're looking at in order to determine if there's an outside net force is not if it's moving, because an object can stay in motion without a net force being applied, but we're looking for a change in that motion. So if it's accelerating, then there's a net force. Now this kind of contradicts what we think. If we drive in a car, obviously we have to keep our foot on the accelerator to keep the car moving. Now this makes sense because you have the force that needs to be applied that keeps the car moving. Now that's what we think, but what we forget about is we have air resistance pushing against the car in the opposite direction. So really we have our foot on the accelerator not to apply a force to keep us moving, but more so to apply a force that balances the force of air resistance. And as long as that force is balanced, we'll move at a constant speed. An object at rest will stay at rest. You don't expect an object to all of a sudden just jump off the counter without somebody applying a force or something applying a force in order to cause that motion. So an object that's moving will continue to move with no friction. An object will continue to move at the same speed or stay at rest. So the examples I have here is a ball that's rolling with no friction. Now a lot of times we don't talk about balls that are moving with no friction because the friction is actually what causes the rolling. A hockey puck that's sliding on ice. Now ice is kind of a term that we use, or a surface that we use to talk about very, very low friction. Ice really does have friction on it, but it's very, very low as compared to what we're used to as far as surfaces that we usually walk on. And then a book sitting on the desk, well, that object's going to sit still unless some force is being applied to it. So this is an example of Newton's first laws where we have no friction being added in any one of these scenarios, so the object will continue moving at a constant speed or sitting still until some net force is applied to it. This is going to be an example of Newton's first law. There are actually two parts of Newton's first law. It says that an object at rest will stay at rest until an outside net force is applied to it, or an object in motion will stay in motion until an outside net force is applied to it. So the first one, an object at rest, as long as there's no net force being applied to it, meaning all the forces are balanced, then it's going to stay at rest. But if we remove one of those forces, that means there's going to be a net force. And then that net force is what brings it down. All right? So it starts accelerating. So an object that's at rest or in motion. Now you can see this object, as it travels, it looks like it's moving relatively at a constant speed. But it'll stay at that constant speed until a net force is applied to it, like the end of this track. Now you may notice it starts slowing down a little bit. It shouldn't be too much of a stretch to say that the reason it's slowing down is because there is a force of friction acting on it. So if you can imagine, if there were no force of friction, this object would continue moving at a constant speed the whole time. So that deals with Newton's first law when an object is in motion. And really, speaking about objects that are in motion or at rest, both are actually the same thing. An object in motion has a velocity, an object at rest has a velocity of 0. So really it's just saying that anything that has a constant velocity will continue to have that constant velocity until a net force is applied to it. So an object in motion will stay in motion until the net force is applied, an object at rest will stay at rest until a net force is applied. So here we have the two laws we just talked about. Newton's first law for every object that's in motion or at rest will stay in motion or at rest until an outside net force is applied to it. It's called the law of inertia. Newton's third law: for every force, there's an equal and opposite force that's being applied. Equal in magnitude, opposite in direction. And Newton's third law talks more about only two objects. For example, if I say that a book sitting on a desk has a force upward from the desk and a force downward from gravity, I wouldn't say that's Newton's third law, because the force upward is from the book and the table, and the force downward is being caused by the gravity of the earth. Now that takes into effect three things: the table and the book. That's two things, and then you have the gravity of the earth, which is the third thing. Newton's third law talks only about two objects. So the force of the table applying on the book, there's a force of the book on the table. So you take those two objects, you switch them. That's how you get the second law of Newton's third law. Now, if you notice, we don't have Newton's second law here. There's going to be a lab that we do in class that'll show Newton's second law.